Have you noticed how a top student isn't strong at only one subject, but he balances all subjects together? That balance gives him stability and success. In the same way, benzene isn't stable because of its only one structure. It is because of resonance phenomena. Hi, I am Dr. Swathi, your organic chemistry coach. Resonance in benzene is one of the most important expected question in your university exams. So save this video right now because today we will break down resonance, resonance energy and orbital structure of benzene in the simplest way possible. So stay with me till the end of this video. So resonance is a phenomena in which a molecule can be represented by two or more Lewis structures which differ in arrangement of electrons. That means some molecules can be represented by two or more than two structures, and those structures will be having differences in the electronic arrangement. So the resulting structures in this case, they are known as resonance structures. Now let us consider resonance in case of benzene. So the resonance structures of benzene are given by Kekulé. So it has two resonance structures. So this is the first resonance structure of benzene. The benzene molecular formula is C6H6. So that means it has 6 carbons. So using these 6 carbons, first make a hexagon. Now benzene has 3 double bonds in its structure. H6 means there will be 3 double bonds will be present in the structure of benzene. So keep these 3 double bonds at alternative positions like this. Okay, so that is how we can make the first Kekulé structure. Now this structure has one more resonance structure. The molecular formula of the resonance structures will be same, but they differ only in electron arrangement. So just by shifting the double bonds in this first Kekulé structure of benzene to the adjacent positions, we can get one more resonance structure of benzene. So this one. So how we got this second resonance structure? That is by shifting the electrons, the pi bonds which are present in the first structure to the adjacent position, we can write the second structure. So this is how we can draw the resonance structures of benzene which are given by Kekulé. The original structure of the benzene is neither structure 1 nor structure 2. These two Kekulé structures are the hypothetical structures of benzene. Okay, so the original structure of the benzene is represented with the help of resonance hybrid. Now how we can draw this resonance hybrid is by combining both the resonance structures. All carbons in benzene are equivalent, so we can start numbering the carbon atoms from any position. Just to understand how we can write the resonance hybrid, I have numbered the benzene like this. Now in the first resonance structures, double bonds are present at first position, third position and fifth position. When it comes to the second Kekulé structure of benzene, here they are present at second position, fourth position and sixth position. It is like benzene is having double bonds at all positions, 1, 3, 5 in the first structure, 2, 4, 6 in the second structure. And these two structures are chemically equivalent. That means if you combine both these structures, it is like the double bond will be present at all carbon atoms in benzene. So we will show the delocalization of these pi electrons across all the carbon atoms. So that is how we will write a circle inside this hexagon. So that is how resonance hybrid will be represented. In structure 1 and structure 2, the double bonds are localized. That means we are keeping double bond at one position. But originally, if you see, these pi electrons will be delocalized throughout the carbon chain, which can be best explained with the help of resonance hybrid structure of benzene rather than the Kekulé structures of benzene. It is because of this delocalization of pi electrons and the resonance phenomena, benzene is stable. Such type of molecules will be having a typical energy which is known as resonance energy. So what is this resonance energy? It is the difference between the energy of real molecule of benzene, that is the resonance hybrid, and the hypothetical Kekulé structure which is having localized bonds. So the energy difference between these two structures is known as resonance energy. And the resonance energy of benzene is 36 kilocalories per mole or 151 kilojoules per mole. So it is represented in terms of kilocalories per mole or kilojoules per mole. So greater the resonance energy, greater will be the stability of the molecule. It is because of this large resonance energy, benzene is exceptionally stable when compared with other unsaturated compounds. And it is because of this reason, it will undergo substitution reactions rather than addition reactions. That means it is because of this resonance stabilization, it will resist addition reactions. Now let's discuss about the another important phenomena, why the original structure of benzene is close to resonance hybrid rather than the cake-like structures of benzene with the help of bond lengths in benzene. The geometry of benzene is established with the help of X-ray crystallographic studies. And from the results, the scientists came to know that the carbon-carbon bonds which are present in benzene are neither having single bond character nor exactly having double bond character. So if you look at the values, carbon-carbon bond lengths in case of single bonds is usually 1.54 angstroms, whereas carbon-carbon double bond length is 1.34 angstroms. When it comes to benzene, all carbon-carbon bond lengths are equivalent to 1.397 angstroms. Means they are having intermediate bonds and the value is somewhat near to the double bond length. So based on that, we can say that all carbon-carbon bonds in benzene are having double bond character. So these results further evidences that the original structure of benzene is a resonance hybrid structure. So based on all these phenomena, we can say that benzene is stable because of the resonance phenomena. And why benzene is exhibiting resonance phenomena is because of the delocalization of pi electrons throughout the carbon ring system. Now we'll see with the help of orbital structure of benzene how this delocalization of pi electrons occurs in benzene. So this is the structure of benzene. And now you can see there are 6 carbon atoms are there. So if you look at the hybridization state of each carbon, so each carbon is a doubly bonded carbon as I mentioned earlier. So always doubly bonded carbon atoms will be in sp2 hybridization state. So all the carbons of benzene are in sp2 hybridization. So here one s orbital of carbon, it intermixes with 2 p orbitals of carbon and thus results in the formation of 3 sp2 hybrid orbitals. And these 3 newly formed sp2 hybrid orbitals will be arranged as if they are pointing out the corners of a triangle. So at each carbon, there will be formation of 3 sp2 hybrid orbitals and along with that, there will be one unhybridized p orbital left over. So how exactly this sp2 hybridization occurs across doubly bonded carbon atoms? I have made a detailed video where I have explained about the formation of sp, sp2, sp3 hybridizations. And that video link is given at the end of this video. And for clarity, go and watch that particular video. So with respect to each carbon atom, it will be trigonal shape. But all these 6 carbons, when you put together in the form of cyclic ring form, ultimately we are going to get a flat molecule, which is a symmetrical hexagon in case of benzene. Now let us see how these 3 hybridized sp3 hybrid orbitals and one unhybridized p orbital at each carbon are going to participate in bonding and finally giving the structure of benzene. Now let us see how we can draw orbital structure of benzene. So to begin with, first write all 6 carbons like this. Then show 3 sp2 hybrid orbitals at each carbon atom like this. So at first carbon, let us say 1, 2, 3. The arrangement of these sp2 hybrid orbitals will be trigonal in shape. So in this trigonal shape, now let us draw the sp2 hybrid orbitals at each carbon. So this is how at each carbon atom there will be 3 sp2 hybrid orbitals. So when you are writing these sp2 hybrid orbitals across each carbon, you can see the sp2 hybrid orbitals of neighboring carbon are involved in overlapping. So this is how the hexagonal structure of the benzene is obtained because of the overlapping of sp2 hybrid orbitals of the neighboring carbon atoms. So this sp2 hybrid orbital, which is left over at each carbon atom, will be overlapping with the s orbital of hydrogen. So this is how, due to the overlapping of sp2 hybrid orbital of carbon and s orbital of hydrogen, there will be formation of 6 carbon hydrogen sigma bonds. So this is how these sigma bonds are obtained. Now, in addition to these 3 sp2 hybrid orbitals, each carbon will be having one unhybridized p orbitals. So let me draw that p orbital. The unhybridized p orbitals will be arranged like this. It is shown with black color dumbbell. So the remaining unhybridized p orbital at each carbon overlaps sideways with the adjacent p orbitals. So because p orbital has 2 lobes, with respect to the upper lobes as well as the lower lobe, the delocalization of electrons will be shown. So this is how the delocalization of electrons will be shown with the help of a circle which is drawn very close to the ring carbon atoms. It is because of this delocalization of pi electrons, benzene is stable and it is exhibiting resonance phenomena. So in summary, the exceptional stability of benzene is due to the resonance phenomena and it mainly arises because of the delocalization of pi electrons. Kekle has given two resonance structures for benzene and which can be best represented by its resonance hybrid. The resonance energy of benzene is 36 kilocalories per mole. All carbon-carbon bonds in benzene are having double bond character, which is evidenced with the help of X-ray crystallographic studies, and all carbons are in sp2 hybridization state. Now that you have learned about resonance energy, bond lengths, and orbital structure of benzene, if this video is useful to you, then like it, subscribe my channel and share to your friends. Thanks for watching. Stay tuned to my next videos.